Here, some question. Yeah.
Sir, this is a bit of a vague question, but quantum mechanically, angular momentum and charge, which are part of the no-hair theorem, are like quantum numbers.
Yes.
And let's say I take another quantum number like isospin, strong isospin, or color charge, something like that. How are they lost in this? Like, for example, how do I lose count of my iso charge or some other quantum number, something like that, in the black hole?
Yeah. You know, it's an interesting fact that no global symmetries are conserved in a quantum theory of gravity. Okay? And one colloquial way of saying this, one simple way of understanding this is precisely what you just said. That, you see, when something's absorbed into a black hole, it remembers all the gauge charges. Because gauge charges have their cause electric fields, which you can measure even outside the black hole. Okay? However, black hole forgets all details of all conserved charges, of all globally conserved charges, charges that are not coupled to gauge field. So if you have a black hole that, you know, if you have a symmetry that in the absence of quantum gravity was conserved, you have a black hole that is made up of charge q of that symmetry. That black hole is not different. The solution for that black hole is not different from an uncharged black hole. Once all the stuff has fallen in, the outside world forgets about it. And so then presumably the Hawking radiation is blind to that charge. So once the black hole is evaporated, the charge has been lost. So that's one way of understanding why global charges are not conserved in quantum gravity. But it's it's a fact that is independently believed to be true. Yes.
A black hole can never be destroyed without doing something clever and quantum. Clever and quantum. So what are you trying
What
to...
did I mean? What did I mean when I wrote those words? I'll tell you what I mean. Okay. You know, this first theorem that the area of a black hole can never decrease is a pretty robust theorem. The second theorem that that horizons cannot bifurcate is a general relativist theorem. What I mean by that is that you make some assumptions and then you prove it. Now, one of the assumptions you make in proving this is about the nature of future event horizons. It's a bit of a shady theorem. You know, you assume that event horizons don't do bad things, and then you use that to prove that event horizons don't do bad things. Okay? The true statement is that within general relativity, without meeting some sort of singularity in general relativity, this will not happen. But it's not so clear to me that it means actually that will not happen. Okay? So imagine this. Suppose you've got a black hole. It's got an event horizon that's doing this. Now you bang it hard enough. If it tries to do this and separate out, within general relativity there's some sort of singularity. But you know, same thing is true of soap bubbles. You take a soap bubble, you bang it, it'll go like this. At some point, soap bubble fluid dynamics will not be valid when it does this. But it doesn't mean that this will not happen. Okay? So that one black hole can never break up into two or more is true within some caveats in general relativity. It's not totally clear to me that it's true about reality. That's what I meant to try to say.
So I thought that you meant that quantum is not clever. It's clever and quantum.
No, that's too deep an interpretation.
You mentioned that if you hit a black hole, it will slowly decay and get to a stable state.
Yes.
But in case of any external perturbation of a black hole, the Cauchy horizon may turn into a singularity by the blue shift mechanism. In that case, it follows some exponential growth of the amplitude of the perturbation, which may happen in case of the superradiance in case of Kerr black hole.
Okay. Now, as you know, for Schwarzschild black holes, there's a theorem, right? The theorem is that at least for reasonably small perturbations, they all decay exponentially. Something like superradiance does not happen. Kerr black holes in a box, okay, can be superradiant, but I think four-dimensional Kerr black holes, at least in the absence of a black box, are just stable. Now, it's true that if you take like curved black holes in ADS or maybe in higher dimensions, there may be some issues. But I think 4-dimensional curved black holes, as far as I'm aware, are absolutely stable. Is that wrong? The inner horizon, of course, has instabilities for the curved black hole, but that's not what we're talking about. You're talking about the inner horizon. Is that what you're talking about? That's irrelevant. We're talking about the outside the outer horizon.
But depending on the different characteristics of the black hole, the outer horizon, the decay rate of the outer horizon perturbation, that also follows sometimes it decays exponentially, sometimes it decays
Power law, you're saying.
In power law of
price
R.
business, price
Yes.
law kind of thing.
So there's some competition between the exponential growth and the
What
decay.
growth? There's no growth for the outer horizon.
Not for the outer, but for the
You see,
inner.
what happens inside the outer horizon does not affect what somebody outside sees. Okay? Because of causality, what happens inside the outer horizon makes no difference to somebody outside the black hole. Okay? So when I say stability of a black hole spacetime, I mean stability of the part that is outside the outer horizon. Stability of the part that is accessed by an asymptotic observer. What happens inside, near an inner horizon, near the singularity, is interesting but irrelevant to this question. But thank you for the question.
Hello, sir.
Yes.
Sir, actually my doubt is event horizon production and black hole are simultaneous event, or they first singularity is produced afterwards the event horizon is produced? Because it's one of idea I just came across.
Yeah, it's a very, very interesting question, one that is much debated. The question that is being asked is, are all singularities always shielded by event horizon, so you can't see them from the outside? Or does it happen that in some collapse processes, you have a singularity that for a while is visible from the outside and then perhaps eventually shielded by an event horizon, or maybe not at all? This is a much debated question, okay? In fact, my colleague in TIFR, Pankaj Joshi, has written many papers claiming that the first is true, that in realistic situations, singularities can sometimes be naked, can sometimes be visible from the outside. However, let me take, since you want my opinion, I'm giving you my opinion. I think the safe set of data comes from not looking at phenomenological models or models like fluid dynamics coupled to gravity, which is what Pankaj does. But instead looking in situations where the equations you use are those of fundamental physics. Why is that? That's because you see, equations like hydrodynamics are only valid on a certain length scale. So if you can show that hydrodynamics coupled to gravity leads to a singularity, all that you've reliably concluded is that hydrodynamics coupled to gravity leads to singularity within the hydrodynamic approximation, and therefore a singularity on the scale of the mean free path of the fluid. That singularity may well be resolved at smaller scales. So the safe thing to do is to use more fundamental looking equations. Now this has been done for many years. People have tried to study the collapse of scalar, for instance, a scalar field, a minimally coupled scalar field coupled to gravity, in much the same way that people try to produce naked singularities. And this led to this famous result by Choptwick. And the Choptwick result was as follows. Suppose you take a shell of scalar stuff and you let it come push in. Let's fix the mass of the shell and keep varying its thickness. So just take any one parameter and keep varying it. Okay? So you've got a one parameter set of initial conditions. What happens? Well, if the shell is big and fluffy compared to the mass of the black hole that would eventually be formed if all of the shell was put into a black hole, then gravity is effectively weakly coupled for this problem and nothing happens. The shell just goes through and it's like behaves free. If the shell is very thin, it just effortlessly comes within its event horizon before it realizes that the rest of the shell collapses to form a black hole. The question that Choptwick and company asked, and in my opinion convincingly answered in series of simulations, is how does the transition between these two regions happen? Is there a region in the middle where something funny happens, like this naked singularity? What they found was that it's sharp. There's one set of initial conditions for which the first happens. No event horizon forms. No singularity. The second set where an event horizon and a singularity forms. if you're on that, the phase transition is like a second order phase transition. So if you're at the boundary, you indeed do get a naked singularity. Okay? But infinitesimally here or here away from the boundary, you don't. If this is the data we will take to draw lessons, as many people do, we would conclude that naked singularities can form, but they require fine-tuning. They require you to take a number and set it to exactly some value. It depends on your model. In what I described, it's true, it would be a point-like event. But in some of Pankaj's models, there are naked singularities that last forever. Or at least some people's models, I'm not sure. Some people's models, there are naked singularities that last for a long time. But it's true that in many scenarios that people try to constrain, it's just a point-like thing. But even the formation of that point-like thing generically, that is for initial conditions that are not enormously fine-tuned, that will actually happen with the actual equations of physics in the world is far from clear to me. Or actual reasonable equations, meaning fundamental type equations. Far from clear. Yes.
So after this.
Sir, here. Suppose we make one thought experiment. Suppose a particle is entering in the event horizon.
Yes.
Will it possible the quantum tunneling that there is a probability that it will not enter in the event horizon or it will pass it, just like quantum tunneling? Will
Yes.
it possible?
Yes. Are you asking whether there is some chance that it will not?
Yeah.
Okay, it's a very good question. Sure, of course there's some chance. But, okay. However, the amplitude that this happens would be further and further suppressed as the particle goes deeper and deeper into the black hole. Now, this suppression would happen exponentially in e to the power 1 by h bar. So it would be a very small effect, much smaller apparently than Hawking radiation, which is only power law in h bar. So I don't think it doesn't seem like this is what's going on. And maybe your suggestion is that this is what's responsible for recovering information. And maybe that's true, but it would be nice to put some equations to it.
So when the red giant goes on supernova, so you have shown that it is can go for black hole or a neutron star. It is a random possibility, or it depends on the properties of the red giant.
No, of course, it depends on the properties of the red giant, in particular its mass. Right? I mean, if it's big enough, it will become a black hole. And it doesn't radiate, it's a very complicated process. Firstly, I should say that it's a very complicated process because this thing collapses and then it triggers some sort of explosion in which it loses some fraction of its energy and so on. But if the remnant mass is large enough, it will always form a black hole. So one of the important determinants is the mass.
Sir, what is your view on a supermassive black hole? They should be exit or no?
How supermassive do you mean by supermassive? What do you mean by supermassive? Give me an estimate of mass.
One of the 70 billion mass of sun.
70 million, sure they exist. We saw one, right? This one. This is 4 billion masses of the sun. They definitely exist. I mean, might be.
Excuse me, sir. You told that area of event horizon cannot decrease; it can only increase.
Yes.
And also, the black hole cannot be destroyed into two parts, right?
Yeah.
So, in which case, area could be increased?
What?
So, event horizon area could be increased. You told that.
It can increase, but cannot decrease. Yes.
So, in which case, it could be increased?
Increase is no problem. You take a black hole, you throw, you jump in. Its event horizon area will increase. It becomes more massive.
So, it will radiate an energy and then.
Yes, it will radiate, but there are time scales. The time scale for radiation, which is a quantum time scale, is very, very long. The time scale for the increase of the event horizon is a classical time scale, which is much shorter.
Adding to that, you also mentioned about the entropy, and it was C cube A by 4GH. Okay, but it's a constant, right? It can never increase, even if the area increases of the black hole.
Go on.
Even if supposedly if someone goes into the black hole and its area increases, but our entropy is a constant, right?
What do you mean our entropy is a constant?
See the formula, C cube A, you said the
A can increase.
Oh, okay, okay.
You see, this had a lot of constants of nature, but A was not one of them.
So,
Yes.
okay, my question is this. I've heard somewhere that galaxies have like massive black holes at their center, but these are dormant. So how at which point would we say that a black hole becomes dormant?
This goes beyond my knowledge. One of the astrophysicists here, maybe Tarun can explain.
Black holes have an active phase in the life when they're eating up matter around it. When they finish their lunch, they go down dormant. So that's typically what it is. And because while they're eating, they spew out one of the most energetic phenomena, in electromagnetism are these active galactic nuclei, and you need a black hole to fuel such, falling into a black hole to fuel such things. But that's minuscule compared to the kind of energies that gravitational wave coalescence generates.
So the first theorem of general relativity says that area of black hole can never decrease.
Yes.
Right? My question is, when two black holes collide, they merge into a bigger black hole.
Yes.
Yes. So consider a case where two single drops merge into a single bigger drop. Their area of the total area of bigger drop is less than the sum of the two areas of the smaller drops, right?
Yes.
So in that case, we have lost area of event horizon when two black holes are colliding and merging into a single big black hole.
Yes, but the geometrical formula that govern drops of liquid are not the same formula that govern black holes. Let's quickly do the calculation. Okay, so a black hole in 4 dimensions of mass m has radius of order m. Okay, and so its area scales like m square. Okay, now let's say that you double the mass of the black hole, you increase the area by a factor of 4. Okay, so suppose I took m that had m square and m square, so 2m square. But if I took 2m and then squared it, I get 4m square. So its area has increased.
Sir, when neutron stars collapse and become black holes, so the neutrons, whatever they do, whatever they form, must form fermions only. So, but how come the Pauli exclusion principle get violated after that, even if they are fermions, or is it not a fundamental principle?
No, it is a fundamental principle, but what's happening is this. It's never happening that two objects are sitting in the same state. As you make things smaller and smaller, all the objects are always going to distinct states. It's just that these distinct states go to higher and higher energies. Okay? So the thing that would like to prevent that from happening is you see, that requires larger and larger pressure. To send things to high energy requires very large pressure. Things don't want to spontaneously go to very high energies. However, we're in a situation where the desire to go smaller because of gravity overwhelms that. I can't, who asked the question? Yeah. Okay, this is precisely the calculation that Chandrasekhar did. At any given step, until it's reached 0, where it becomes hard to say what's happening, at any given step what's happening is that the neutrons are always obeying Pauli exclusion principle. Okay, they're always obeying this exclusion principle and therefore becoming more and more energetic. Okay, suppose there were only 3 states, 3 fermions of momenta 1 by r, 2 by r and 3 by r. Okay, these were the 3 lightest states. Okay, so the energy which is like momentum square would be like 1 square plus 2 square plus 3 square, which is whatever it is, 14 by r square. And always these things, these neutrons will occupy these 3 distinct states. As r becomes smaller and smaller, they have to go to crazier energies. Okay, the energy will be 13 r square, always obeying Pauli exclusion principle. But not even this fact that it costs so much energy to make this thing smaller is enough to prevent the gravitational collapse. Okay? So the fact that there was a barrier, there was some pushback, was due to the Pauli exclusion principle. But that is not strong enough. So in the calculation, it's never violated, and yet it crunches to 0.
Thank you. Thank you.
So the theory is that the black holes are always sucking stuff and everything is collapsing in, whereas there is also other theory that universe is expanding.
Yes?
So how are both possible at the same time?
They're basically unrelated phenomena. You know, a black hole is something that on some length scale, and let's say you've got 2 black holes. This black hole could be sucking stuff and eating stuff up, and the universe could be either expanding or contracting or doing whatever it wants. This is a local thing that's about the whole universe. These two are basically unrelated things. Is there a theory of white holes? White holes are very interesting objects. Okay, what is a white hole? Okay, you know, through my talk I talked about things that seem to violate a basic principle of physics, namely that the fundamental equations of physics have a symmetry between t and minus t. Time and minus time. You know, I told you that the area of an event horizon always increases. Well, it increases in positive time. But doesn't that violate the fact that in fundamental equations of physics, t and minus t are the same? How does that work? Okay, so with this in mind, let's ask, what is a white hole? Suppose you've got a solution, okay? Suppose you've got a solution which describes collapse into a black hole. You can take that solution and just reverse time. Because time reversal is a symmetry of the fundamental equations of physics, that will continue to be a solution of Einstein's equations, but will describe something else that is very funny. It will describe a universe that started off with a singularity, and in which the singularity vanished because of some weird stuff. Now, this is formally a solution of Einstein's equations. That's certainly true. But it's a solution that requires a particular kind of initial condition. Okay? Seems unclear that there is ever a physical situation in which those initial conditions are relevant. On the other hand, the black hole solution is always relevant because there are very reasonable initial conditions, like a star losing fuel, that form black holes. Okay? So white holes are solutions of Einstein's equations, not yet clear what physical implications they have in the real world. I should say, though, that my answer is a bit simplistic. In various theoretical situations, for instance, in the description of the thermofield double of n equals 4 Yang-Mills theory, eternal black holes play a role. Eternal black holes have both black holes as well as white holes. So in certain theoretical situations, they're interesting. But it's not clear that they're real objects in the real world, or what it would mean. There's some similarity between a white hole and a cosmology. Maybe there's something interesting to say.
Oh, hi, sir. So my question is not about the science behind black holes. My question is why the black holes are having such a overhyped or oversized image among all.
You tell me. I mean, you know, they're fascinating things, right? You get into one, you can't come out. They produce 3 solar masses of energy in 1,000th of a second. And they're objects that do all these dramatic things while in some sense being very simple, while being described by what are, in my opinion, the most beautiful equations ever written down by human beings, namely R mu nu is equal to 0. Let's contrast 2 phenomena. Let's contrast these 2 black hole collisions, the LIGO black hole collisions with a supernova explosion. Both are very grand, dramatic events. Both are very interesting. In order to model a supernova, you need to keep track of so many things. The detailed structure of what's going on. However, this other grand event is so simple. Black holes, okay, I should we could have a longer conversation about this offline.
You have said that light comes near to the black hole, it comes get pulled into the black hole, right?
Once it goes past its event horizon, it has.
So what is that which is faster than light? It pulls lights it inward.
It's a good question.
What is that?
What is that?
I am that curious about it.
Yeah, it's somehow the structure of space-time. You know, in the mathematics, there isn't anything there. Light is moving on a manifold. The manifold has this nature. It's not like there is something that is pulling it. It's the base on which the light is moving has this funny property that in some sense is falling in. I know what you're asking. I don't have anything clear to say.
Sir, but you give an example of.
Yeah, you should be careful. You should be careful. Those analogies are just analogies. Okay? And they have their weaknesses. This is one of them. Yes.
Sir.
Yes.
Sir, it is possible to make black hole in labs.
Is it possible to make black? I hope not. I mean, what people do is to make fluid dynamical black holes. What? Who are you talking about? These black holes in a sink, those kind of things? Yes. So it's possible to do the following. What? Scottish labs. They couldn't have made a real black hole. It must be some analog of a black hole. You know, you make a black hole, you know it, right? Okay. No. Yeah. Let me tell you about what is done. People do experiments on what are called black holes in a sink. They do experiments on fluid dynamical configurations that are very similar to the analogy I produced. Okay? And actually, there is even a proposal that Hawking radiation in a situation like the one I proposed could be measured in a lab, and people get very excited about that kind of thing. To the best of my knowledge, there isn't a serious proposal to make a real black hole in a lab. I mean, you may call things black holes, but they're not black holes.
Okay, so, Shiraz will never get tired, as it can go up to 10, 12, but I'm getting some indication to stop, but probably one very urgent question maybe. So, someone who raises his hand first.
Good evening, sir. This would sound like a very trivial question, but how do we measure the mass of a black hole? I mean, it changes, it keeps on changing, right? How do we characterize it?
Why do you say it keeps changing?
Because, okay. But then how do we determine the mass?
You measure the mass of a black hole like you measure the mass of anything else. You look at something orbiting it, and you deduce from the orbit what mass it has. How do you measure the mass of the sun? We can estimate the mass of the sun by looking at the time period of the orbit of the Earth. Okay, something like that. Mass is something that leaves its imprint at far away, because of Newton's law, essentially. Mass sources warping of space-time, and you measure it that way. Technically, there's this thing called ADM mass in general relativity, which measures the deviation of the metric from flat space at infinity that measures the mass. But what that's really saying is you can measure mass by seeing how it affects things moving around.
Okay. And so one more thing, actually, when we consider the imbalance of antimatter and matter in the universe, you mentioned about pair production at the event horizon. So is it possible that the antimatter particles went into the event horizon while they were when the pair production was going on, and then the matter particles, they were left behind?
What you need is a source of CP violation, and black holes don't violate CP in that way. You can discuss this in more detail, but I don't think that's right.
Thank you, sir.
Okay, so let us thank Shiraz for this wonderful talk. So this is a small memento from all of us to Shiraz for his wonderful talk.
Thank you.
And hopefully he will keep coming here, and we'll have a lot of opportunity to talk to him. Thank you, Shiraz.
Thank you, sir.